Hey everyone, it's Chad here. Today we're tackling the LeetCode problem 417 Pacific Atlantic water flow. I'll walk you through how I'd solve this in a coding interview, from understanding the problem and devising a plan to coding, testing for errors, and evaluating time and space complexity. I'll be solving this problem in Python, and I'll think out loud and ask clarifying questions just like in a real interview scenario. Let's get started. So, first of all, to better understand the problem, let's start from the problem statement. So, there's M times N rectangular island that borders both the Pacific Ocean and Atlantic Ocean. The Pacific Ocean touches the island's left and top edges, and the Atlantic Ocean touches the island's right and bottom edges. So for the M times N rectangular island, we do have this, where we have M rows and N columns, and we have the Pacific Ocean as said before, that touches the top and the left edges, while the Atlantic Ocean that touches the right and the bottom edges. The island is partitioned into a grid of square cells, where we do have M times N cells. So each of those cells has heights, where heights row column represents the height above sea level of the cell at coordinate RC. So if I do have this cell, well, it just means that the cell at the row 2 and column, row 1, because it's 0 indexed, and column 3 has a height of 4, right? The island receives a lot of rain, and the rainwater can flow to neighboring cells directly north, south, east, and west if the neighboring cell's height is less than or equal to the current cell's height. So, so in this island that is divided into different cells, we do have some heights, and we do have a lot of rainwater everywhere. And what this sentence gives us is that when some rainwater rains, when we do have some rainwater, let's say in this cell, it can flow to this one, to the north, to the west, to the east, and to the south, because each of those has heights that are lower compared to this one. And we want to return a 2D list of grid coordinates result, where result I gives us the row and the column that denotes the rainwater can flow from RICI to both the Pacific and Atlantic Oceans. Okay, so if I sum it up, as input, I have this heights, right? Where heights row column gives us the height above the sea level. And the output is actually results result I, that is also row column, where rainwater can flow from RC to both Pacific and Atlantic Oceans. Right, let me put this. There we go. First of all, okay. Okay, we want to list all the rows columns that can flow both to these Atlantic Oceans. So I think I would subdivide this. I would divide this problem into two different situations. So I can first find all the rows and columns that can flow, where rainwater can flow to Pacific. Then I would cells where cells where rainwater can flow to Atlantic. And then I would, maybe I can return them as sets, as a set. And then I can make an intersection and return a list. Okay, so yeah, that's one thing. And the second thing, when I see this problem, is that we'll be using a BFS, breadth first search here. Because let's say I'm starting from, so to know all the cells that can reach Pacific Ocean. And actually, I would initialize the queue. So, you know, the first ones, with all these cells for example, Pacific Ocean, I would initialize the queue with all the cells from row equals 0, right? If row is equal to 0, we end up with the first line. And then I would also have, I would also have all the cells from the first column, right? And in the BFS, whenever I start from somewhere, I know the directions, right? So it's given in the problem statement where directions are going to be north. So north is represented by -1, 0. South is represented by 1, 0. Right is represented by 0, 1, and west. And east, east is represented by 0, 1, and west is represented by 0, -1. So these are the directions, right? And how would I find the neighbors? Well, for each cell, the neighbor, so the neighboring row and the neighboring column would be row plus dr, where dr is actually the direction row, and column plus dc. So for each row, I can easily get the neighboring cells this way. And I would append them into the queue if they are not yet visited, right? And if they are valid, right? Yes. So if I start with this one, let's say, so I'm looking into all the neighbors. So how do I start with this? So we would put this into the queue first, and then I would pop it out. And when I pop it out, I know that I'm here. And then I consider all of its neighbors. And if all of those neighbors aren't yet visited, and are valid, and when I say valid, that means that they are in the bounds. For example, for this one, the not does not exist, right? And I have to know if I can get to that that cell that is using the condition of can flow to, that is its height is lower than or equal to this is its height. And if that's the case, so I can move forward, I would append it in the queue. And whenever I consider any of these okay. Yep. So this is one way of doing. But now that I think about this, actually, I talked about the fact that we want to find all the cells that can float to Pacific, right? But initially, we start with we know a list of cells that already we know that can reach the Pacific Ocean. So we can actually see this problem the other way around. So if we can find from this cell what are the cells that can reach that the water can flow from, then we can extend slowly all the cells that can reach Pacific Ocean, for example, and return them, right? So let's do this way. Now that I've understood the problem, let me carry out my solution. And I've already also devised a plan because I'll be using a DFS. And what I'll be doing is, first of all, so let me sum it up here. First of all, what would I be doing? So I'll define a method, right, is valid. That'll give me if the given row and is valid, right? So this is pretty simple. We would be returning if row is between m and this one is between n 0 and n, and where we have to define m and n, where m is length of heights and n is length of heights 0. So we have to confirm one thing here. Can heights be empty? That's one my question here. And let me look into the constraints. So yeah, we can see here that mn is always superior to or equal to 1. It's higher than or equal to, greater than or equal to 1. So this is not a problem. Now that I do have this, I can have this. Yeah. And one other sub-problem that we want to solve is given a cell, right? Given can flow from so I have a start and an end. I want to return if start heights, right? So we look into that row, that column. So I'm looking into the start cell. So let's say this is the start cell, and this is the end cell, right? And if the start cell's height is superior or equal to end, then that means that water can flow from start to end, right? Now let's define cells can reach cells that reach cells reaching ocean. Not ocean, maybe cells that can reach the queue. So what is this queue? So for me, this queue is actually, this would be the cells that are that we know already reach ocean, right? Cells that reach the oceans or the neighboring. So let me explain what I'm looking into here. I want to actually implement BFS here to actually, so I would be starting from these cells and get all the cells that can reach to these starting cells, because if any cell can reach any of these cells here, that means that that cell can reach Pacific Ocean, right? And that's what I want to find out. So now that I have this queue, I want to first pop out the current cell. So that would be, before that I have to while queue. So we want to continue as long as there's something in queue. And there's one other thing that to note. We know that everything in the queue is a solution, right? So let me create a set that is composed of queue. And let me call this here, for example, for Atlantic, Pacific Ocean, Pacific, for Pacific, for cells that can reach Pacific, well, it is first of all empty. Atlantic, this should be empty too. And for row in range M, so what are we appending here? We are appending to Pacific because row is the one that's changing, right? So it's the first column that we want to put in there. So 0. And for Atlantic, it's pretty different. We want to append the last column, right? So it would be m minus, it would be n minus 1. And let me copy this, because now we want to add, the rows. So it's the column that's changing now. And we want to put for Pacific the first line and the last line for Atlantic. There we go. Now we do have Pacific and Atlantic. And let's return cells reaching Pacific, cells reaching Atlantic, and this one's this one should. So what I'm looking into here, I'm actually, let me just write this. Yeah. So, I want to find out here all the cells that can reach Pacific, and the cells that can reach Atlantic. And how do I do it? I start with the cells that are neighbors to Pacific and the cells that are neighbors to Atlantic Ocean. And then I do a breadth first search to find out all the cells that can actually get up there. So first of all, I know that these cells, for example, for Pacific Ocean, these cells are already in the solution. So I start the result with those. And then I start with the Q. I'm popping it out. So I get the row and column that I get the first element from there because, and then what I do? Once I do get it, I can start this one empty, right? Yes. And I want to, do I have directions that are defined? No. Let me get these directions. There we go. And for drdc in directions, the new row, new column is going to be row plus dr column plus dc, right? This is the new row and the new column. And we want to check if new row, new C is actually valid. Then we want to check if we can flow from new row, new C to the current row. That's what we're searching for, right? Can flow from new row, new C to current row, current C. And one other thing to check is actually before running this is, have we already added that one? And if it's not already in the result, well, in that case, we would add new row, new C into result. And we would also add it to the queue so that we can explore further, right? And when this is the case, I would just return result by the end of the session. And what I would do is I would be returning. So we want to return row and column this way as an for row column in cells reaching Pacific dot intersection. Let me explain what I try to do here. So I'm getting all the cells that can reach. Let me rename this. I prefer this way. So I'm taking all the cells that can reach Atlantic. I'm looking at the intersection between all the cells that can reach Pacific. And I get the rows and columns and make it a list as expected here, and I return it. I started with these queues because these are the cells that can reach Pacific. We know that can reach Pacific, and these are the cells that can reach Atlantic. So we are looking into all the columns in the, all the rows in the first column, all the rows in the last column for Atlantic, all the columns in the first row, and all the columns in the last row for Atlantic Ocean. This is good. Now let's check can cells reach is implemented the right way. So we start with the results being already the queue, because we know that all the cells in here match our first condition. Then, while this queue is not empty, we pop the first element. We look in all directions for the next neighbor. We check if it's valid. So, for example, for this 1, 2, and 3 are possible candidates. And we check if we can flow from the next candidate to this one. So here, as 2 is bigger than or equal to this one, and that's the starting point, it is considered. And we check if it is not already in result. And if it's not the case, then we add this to the result because it's a candidate. And then we append to the queue so that we can explore further. But in this case, none of them will be added because they are already in the queue. But if we look into this one, well, this case is valid, the cell is valid, and water can flow from this one to our current row cell, row colon cell, and it's not yet in the results, so we would add it into the queue and add it as a result in the result, and then we would continue this way. We would iterate. We would be adding this one. We would be adding this one, etc., etc. Yep, and this should work. Let me now try to execute this. There's a problem here. We get not. Oh yeah, and what is not in result. So we are looking into NR and see that is the next row and next column is not in. And we do have a problem here. We have out of range. Let me think about this. So we have heights that is -1, 0, 1, 0, 0, 1, 0, -1, right? And we are getting so first of all, we check if is valid, right? So the next row and the next column is row plus dr and column plus dc. And we check if this is valid. So we check heights as 0 as 1 is greater or equal to n0 n1. Let me just first print out if Pacific and Atlantic are well defined. Yes. So I'm getting actually the first colon and the first line, the last colon and the last line, right? So this is good. And the directions. Oh, this was the problem because I'm not checking for the colon here. So is valid but was not working. Let me now execute this. Yes, it's working. Let's now try to submit this. Yes, there we go. So we've successfully implemented the solution. Let me now discuss about the time complexity and the space complexity here for this, for my solution. So first of all, what I'm doing here is, okay, I'm iterating over these cells. So it's O of M, O of N here. But then for each of them, once I do have that, what am I doing? So I'm going through. So in the queue, I can have up to, let's say I only had one everywhere in the problem in here, so I would end up with having all the elements in there. So the queue would start with m plus n elements, almost, yeah, almost m plus n minus 1 to be exact. And then we would look over their neighbors and we would add them into the result. So the end result will have all the elements in here, right? And then once we've done it, we would do the same on the other side. So we would end up with m times n lookups here, operations, and also the queue can go up to m times n, and we do it this way. And here we, if all of them are results, yeah, we would have m times n. So it's O m times n, O m times n. There we go. That's it.